So, in the last lecture you have observed how to find out the Fourier cosine and Fourier sine transform of a function when the function is defined in 0 to infinity level, and also how to evaluate the value of some integrations. Let us see quickly one particular example again on Fourier sine transform. Here the function f x is 0 when x lies between 0 to a, 1 when it is a to b, and it is 0 for x greater than b, and then we want to evaluate the integral 0 to infinity cos of a alpha minus cos of b alpha by alpha into sine of alpha x d alpha. So, your in solution process Fourier sine transform directly I can find out, you can check it of your own, because this is a simple problem. From here I can write down f x equals this, and the value of the given integral is, now we can derive pi by 2 into f x. I am just showing you so that you can do it of your own also afterwards, and I can find out the value of the other. Once I am putting the value of f x, I can obtain the required result. Now, let us go to the other part, that is how to find out the Fourier transform of a function. Earlier cases, in the earlier lecture we have seen how to find out the Fourier sine transform or Fourier cosine transform of a function. Now, let us come to the Fourier transform of the function f x equals e power minus mod x. Please note this one, e power minus mod x, and then we want to evaluate the value of the integral minus infinity to infinity e power minus I alpha x by 1 plus alpha square into d alpha. So, as you know, Fourier transform of f x, which you can write it as f of alpha. So, we are using three notations. Only capital F of alpha will represent the Fourier transform. For Fourier cosine transform we are using f c of alpha, and for Fourier sine we are using f s of alpha. Please note these three notations which we are using here. And from the definition, the value is 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into d alpha. Here you see the kernel I have taken e power I alpha x. Instead of this, I would have taken e power minus I alpha x also. But since here I have taken e power I alpha x, whenever I will take inverse Fourier transform, then I have to take e power minus I alpha x, and here if I would have taken e power minus I alpha x in inverse Fourier, I have to take e power I alpha x. So, I can take either e power I alpha x or e power minus I alpha x, and accordingly in inverse Fourier this will be changing, only please note this thing. So, throughout in most of the cases we will use here for Fourier transform e power I alpha x, and for inverse Fourier transform we will use the kernel as e power minus I alpha x. So, whenever I am substituting this I can write down, since it is the function, given function is e power minus mod x is given. So, therefore, I can break it into two parts, one is minus infinity to 0. In this case, it will become e power x into e power I alpha x into dx, and plus 0 to infinity, it will be e power minus x into e power I alpha x into dx. So, please note here that since my function is here e power minus mod x, so I have breaked it into minus infinity to 0 and 0 to infinity. In minus infinity to 0, the value is e power x, and in 0 to infinity it is e power minus x. Now, I have to evaluate this integral. So, this equals, I can write down 1 by twice pi into minus infinity to 0, I can make it e power 1 plus I alpha x into dx plus 1 by root 2 pi. I am just separating both the integrals, 0 to pi, 0 to infinity e power minus 1 minus I alpha into x into dx. e power I alpha x into dx. Here also bracket will come over here, not here, please note, because x plus I alpha x. So, it will be e power 1 plus I alpha into x, and here minus 1 minus e power I alpha minus x. So, if I evaluate both the integrals, then I will obtain f of alpha, this is equals to 1 by root over pi into e power 1 plus I alpha into x by 1 plus I alpha, limit is from 0 to infinity, plus 1 by root 2 pi e power minus 1 minus I alpha into x by minus 1 minus I alpha, and the integration is from 0 to infinity. So, once I am putting the value of these limits, then 1 by root 2 pi I can bring it common. One in the first case I will obtain 1 by 1 plus I alpha, and for this case if I put the limit, in this case it will be 1 by, this bracket is closed, 1 by 1 minus I alpha, this I will obtain. So, that if I simplify this, ultimately I will obtain root over 2 by pi into 1 by 1 plus alpha square. So, please note that Fourier transform of the function e power minus mod x, this function is this one. Fourier transform of the function e power minus mod x is root over 2 by pi 1 by 1 plus alpha square, and again I have to evaluate an value of an integral. To evaluate the value of the integral, again what I have to do, I have to take the inverse Fourier transform, that is from here I can write down now using inverse Fourier transform f x equals 1 by root over 2 pi minus infinity to infinity f of alpha into e power minus I alpha x into d alpha. Please note one thing, here I have used e power minus I alpha x because whenever I was finding the Fourier transform, there I have used e power I alpha x. So, please note this thing, in Fourier transform if you use e power I alpha x, then inverse Fourier transform you have to use e power minus I alpha x, or you have to do the opposite one. Now, substitute the value of this f alpha 1 by root over 2 pi into root over 2 by pi minus infinity to infinity 1 by 1 plus alpha square into e power minus I alpha x into d alpha. So, that value of the given integral minus infinity to infinity e power minus I alpha x by 1 plus alpha square d alpha, this is equals to, this will be cancelled, root 2 and this pi. So, 1 pi will be coming over here, this pi will go there, pi into f x, and your f x is nothing but e power minus mod x. So, the value of this integral is pi into e power minus mod x. So, just see it quickly again here. We have to find out the value of this. I am writing Fourier transform of f x equals f alpha as 1 by root 2 pi minus infinity to infinity f x e power I alpha x into d x, and this I am integrating by parts. Once I am not by parts, but since the function is given, I have to break it into two parts, minus infinity to 0 and 0 to infinity. In minus infinity to 0, it will take the value of as e power x, whereas in 0 to infinity it will be e power minus x. So, Fourier transform of alpha I can write down like this, which already I have shown, and ultimately you are obtaining the value of Fourier transform as root over 2 by pi 1 by 1 plus alpha square. So, your f x is 1 by root 2 pi minus infinity to infinity f alpha into e power minus I alpha x d alpha, and that this implies f x is e power minus mod x. So, the value of the given integral will become pi into e power minus mod x. Let us take the another example. We want to find a Fourier sine transform of the function f x equals 1 by x. So, for this one, your Fourier sine transform of alpha, this is equals to root over 2 by pi 0 to infinity sine of alpha x by x into dx. Now, I can substitute here theta equals alpha x. If I substitute theta equals alpha x, this will become root over 2 by pi 0 to infinity sin theta by theta d theta only, and I know the value of 0 to infinity sin theta by theta d theta as nothing but pi by 2. So, that the result of this will become root over pi by 2. So, very easily I can find out the value of this as root over pi by 2 with very simple knowledge that 0 to infinity sin theta by theta d theta is equals to pi by 2. Let us take the next example. We want to find the Fourier transform of this function e power minus s square x square. We want to find out the Fourier transform of e power minus s square x square. So, Fourier transform of e power minus s square x square, which I can write down as f alpha, and this equals 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into dx. Now, substitute the value of f x, you will obtain root over 2 by pi minus infinity to infinity e power minus s square x square minus I alpha x into dx. So, this equals, I can write it to evaluate the integral in terms of square, that is e power minus a x minus I alpha by 2 a whole square plus. So, this will be added alpha square by 4 a square, this is the extra thing. So, plus alpha square by 4 a square into dx. So, this equals 1 by root 2 pi e power minus alpha square by 4 a square can come outside because this is independent of x. So, minus alpha square by 4 a square minus infinity to infinity e power minus a x minus I alpha by 2 a, this is whole square into dx. So, you are obtaining this e power minus alpha square by 4 a square by this thing. Now, to evaluate again this one, if I put this a x minus I alpha by 2 a, this is equals v. I am substituting this thing a x minus I alpha by 2 a, this is equals to this. So, that I will write down Fourier transform of alpha, this equals 1 by root 2 pi e power minus alpha square by 4 a square into 1 by a will come outside minus infinity to infinity e power minus v square into dv. So, this minus infinity to infinity e power minus v square, this is e power minus x square is an even function. Since e power minus x square is an even function, therefore, very easily this you can write it as 2 into 0 to infinity e power minus v square dv. This you can write down. Why I am writing this? Because the value of 0 to infinity e power minus x square dx, the value of this, not this, the value of 0 to infinity e power minus x square dx, this is equals to root pi by 2. This I know. So, therefore, this integral minus infinity to infinity e power minus v square dv, this as e power minus b square is an even function, this I can write it as 2 into 0 to infinity e power minus b square dv, and again I know 0 to infinity e power minus x square dx is root pi by 2. So, effectively value of this integral becoming root pi. So, if I substitute that value, I will obtain 1 by root over 2 pi into e power minus alpha square by 4 a square into 1 by a into the value of the integral is root pi. So, that you will ultimately obtaining 1 by a root 2 e power minus alpha square by 4 a square. You are obtaining this thing, that Fourier transform of the given function is e power 1 by a root 2 into e power minus alpha square by 4 a square, and my function was f x equals e power minus a square x square. This is my f x. So, Fourier transform of this function is this one. Let me rewrite this for some reason. So, Fourier transform of alpha which I obtained here is 1 by a root 2 into e power minus alpha square by 4 a square. My function was f x equals e power minus a square into x square. This was my given function. Now, let us see some special case from here. Some special case, let us check, that is, put a square equals half. What will happen here? Or in other sense, a is equals to 1 by root 2. If I substitute this, then Fourier transform of e power minus x square, Fourier transform of e power minus x square by 2, if I put a square equals this. So, you will obtain a square equals 1 by 2. In that case, you will obtain this value as 4 into 1 by 2. So, that it will be alpha square by 2. Therefore, you can tell that Fourier transform of the function f t, Fourier transform of e power minus x square by 2 is nothing but e square minus alpha square by 2. So, that means, what is this? Is nothing but the function itself. So, basically, if the transform of a function, Fourier transform of a function f x equals f alpha, that is the function itself, then we say that f x is known as self reciprocal. Please note this one, is known as self reciprocal with respect to the given transformation. So, if this condition, if transform of a function is the function itself, then the function f x is called the self reciprocal function with respect to the function whatever transformation we have done. And for this particular problem, please note that you should check it of your own, that Fourier cosine transform of e power minus x square by 2 is equals to e power minus alpha square by 2. Therefore, we can tell that the function e power minus x square by 2 is self reciprocal with respect to Fourier transform as well as with respect to Fourier cosine transform. This problem you should check it of your own, which I am not doing it. So, here we have learned one thing, that is the self reciprocal concept. If the transform of a function is the function itself, then we call that function as a self reciprocal function with respect to a particular transformation. Just like for this example, we have shown that e power minus x square by 2 is self reciprocal with respect to Fourier transform as well as it is self reciprocal with respect to Fourier cosine transform. So, again we will not go to this, we have done it earlier. So, Fourier transform of e power minus a square x square, just using the formula you are finding it out. Then you have to evaluate the integral. So, I am writing in the a square plus b square format. So, I have to make the addition over there. this I am breaking into, I am keeping the e power minus alpha square by 4a square outside. Once I am doing it, I am putting ax minus I alpha by 2a equals b, and I know minus infinity to infinity e power minus b square by dv, since e power minus b square is an even function. So, I can write it 2 into 0 to infinity e power minus x square, and that value is equals to root pi. So, that value we are putting over here. So, root pi by 2 0 to infinity e power minus x square dx equals root pi by 2, and I am getting this result. Now, as a special case, if I substitute a square equals half or a equals 1 by root 2, then Fourier transform of e power minus x square by 2 will be equals to e power minus alpha square by 2. That is, Fourier transform of the function is itself. In this case, if a transform of a function f x is equals to f alpha, then the function f x is called self reciprocal with respect to that transformation. And as I told, e power minus x square by 2 is self reciprocal with respect to Fourier transform, as well as it is self reciprocal with respect to Fourier cosine transform, since Fourier cosine transform of e power minus x square by 2 equals e power minus alpha square by 2. Now, let us see the another problem. We have a function x e power minus x square by 2. We have to prove that this function x e power minus x square by 2 is self reciprocal under Fourier sine transform. For the earlier problem, e power minus x square by 2 is self reciprocal with respect to Fourier transform as well as with respect to Fourier cosine transform. Whereas, for this problem we are telling that prove x e power minus x square by 2 is self reciprocal under Fourier sine transform. Let us see how to prove it. So, Fourier sine transform of x e power minus x Fourier, let me denote it like this, Fourier sine transform of x e power minus x square by 2. This is equals from the definition root over 2 by pi 0 to infinity f x. So, x e power minus x square by 2 into sine of alpha x into dx. So, root over 2 by pi will be outside, 0 to infinity. I can write it as e power x square, just I am writing in other way, x square by 2 into x within bracket into sine of alpha x into dx. So, now you use the by parts for evaluation of the integral. So, that you can write it, this is equals minus e power minus x square by 2 into sine of alpha x 0 to infinity plus alpha into the second integral will come as e power minus x square by 2 into cos of alpha x dx. This we will get, and if I put the values, then I will obtain this equals, this part will not be there. So, alpha into root over 2 by pi 0 to infinity e power minus x square by 2 into cos of alpha x into dx. Please note that once we put the limiting values, the first value of the first integral will vanish. So, in the second integral I am writing alpha into root over 2 by pi 0 to infinity e power minus x square by 2 into cos of alpha x by 2. And please have a look on this integral 0 to infinity e power minus x square by 2 into cos of alpha x dx. What is this? This is nothing but the Fourier cosine transform of e power minus x square by 2. From the definition of Fourier cosine transform of e power minus x square by 2 is root over 2 by pi 0 to infinity e power minus x square by 2 into cos of alpha x dx. So, that this equals, I can write down Fourier cosine transform of e power minus x square by 2. and I know already the Fourier cosine transform of e power minus x square by 2, because just now in the last example we evaluated and we know the value is nothing but the alpha square e power minus alpha square by 2. So, the value will be alpha e power minus alpha square by 2. So, therefore, you see the Fourier sine transform of the function f s equals x, Fourier sine transform of x e power minus x square by 2, we are getting alpha e power minus alpha square by 2, which is the function itself. Therefore, this function is self reciprocal with respect to Fourier sine transform. Please note this thing. Let us take another example. Quickly let us take. We want to prove one thing, that for an even function, just let me go through this one. I am not telling this. Prove that for an even function, the Fourier transform and the Fourier cosine transform are always same. So, if a function is even function, always we can tell that Fourier transform and the Fourier cosine transform will be same. Let us go for the proof. Fourier transform of f x equals f of alpha. This is equals 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into dx. This equals e power I alpha x, you can break in terms of cos and sine. So, that you can write down minus infinity to infinity f x into cos of alpha x plus I sine of alpha x into dx. So, if I write it separately, 1 by root 2 pi minus infinity to infinity f x into cos of alpha x dx plus I will come. So, I by root over 2 pi minus infinity to infinity f x sin alpha x into dx. Now, from here what will happen? Minus, this is the odd function. So, this will vanish since this is the even function. So, this equals, you can write down, this part will vanish because this is the odd function and this function is the even function. So, this you can write down 2 by root over twice pi 0 to infinity f x into cos of alpha x into dx, cos of alpha x into dx. Since, please note, for the odd function this second integral will be equals to 0, and since this is even, therefore, this we can write down 2 into 0 to infinity. So, that I am getting 2 by root over 2 by pi 0 to infinity f x cos alpha x. So, 2 by root over this I can write down root over 2 into pi, and what is this? 0 to infinity f x into cos alpha x. This one is 0 to infinity f x into cos of alpha x dx, and this is nothing but the Fourier cosine transform of f x. From the definition, Fourier cosine transform of f x is equals to root over 2 by pi 0 to infinity f x into cos of alpha x dx. So, that you can write it Fourier cosine transform of f x, and this completes the proof that if the function is even function, in that case the Fourier transform and Fourier cosine transform both will be remain same. Let us see it again here. So, we are just writing starting with Fourier transform of f x, e power I alpha x we are writing in terms of cos and sine. From here I am breaking these two integral. Second integral will vanish due to odd function, and the first integral can be written as 2 into 0 to infinity. So, if I am writing, this will be 2 into 0 to infinity by root over 2 by pi, and this equals nothing but root over 2 by pi 0 to infinity f x into cos of alpha x dx, which is nothing but again Fourier cosine transform of f x. So, for the if the function f x is even function, then always the Fourier cosine transform and the Fourier transform of that function will be same. Thank you.